Today we're starting chapter 8, which goes through a lot of the integration rules that we've already used, plus we'll learn a few new techniques and tricks. So even though this says warm up, we're coming off of a winter break here, so these might be a little bit rusty. We're going to go through them together rather than doing them on your own. All right, so part A, you can see, first of all, you can see these three examples are very similar. There have just been slight changes to the numerator of each problem. Oh, and C should have a dx. That probably got erased. So let's start with A, 4 over x squared plus 9. So you should be kind of running through, like, would u sub work? No, because if u were x squared plus 9, du dx would be 2x, and I don't have an x up here, so that's not going to work. But the more we look and work in this chapter, the easier this is going to stand out. A sum of two squares with just a constant in the numerator, that's an arctangent problem. So if we look at this where u is x, a is 3, and du is dx, we can set up this problem. You can pull the 4 out in front if you want. 4 times the integral of 1 over u squared plus a squared, and then dx can just be du because they're equivalent. And that's arctangent. So how does arctangent work out? Well, we've got 4 times 1 over a, so 1 over 3, times arctangent of the absolute value of u over a. Oh, sorry, it's not absolute value, of just u over a, x over 3, plus c. And we can make the 4 times 1/3 just 4/3. Arctangent of x over 3 plus c. All right, so that's the first one. How does it change in example B when we have an x in our numerator? So it's not arctangent anymore because arctangent doesn't have a variable in the numerator in this case, when you'd have just an x squared, I should say. All right, so let's go back to that u sub idea where u could be x squared plus 9. So then du dx would be 2x, or in other words, du would be 2x dx. Now we have 4x, but remember that's just 2 times 2x. So you have 2x dx, that is du right there, and this 2 can get pulled out in front. If you don't like that, remember you can solve your du dx equation for dx. So dx would be du divided by 2x. If you sub that in, you're going to cancel 4x with 2x, and you'll still get this 2 out in front. Okay, all of that is to say I'm pulling a 2 out in front, and I have 1 over u du. To integrate 1 over u, that becomes natural log of u. So I have 2 times the natural log of the absolute value of x squared plus 9 plus c. And that's as far as we take that one. All right, now part C, what if it's 4x squared in the numerator? So now u sub is not going to work because we need that just to be a 4x for u sub to work. And a technique that we've used in the past, when we had the same degree here, we tried u sub to say like, oh, well, u minus 9 could be x squared, and then can I just sub in u minus 9 for x squared? The problem with that is you still don't have that du satisfied. Du is still 2x dx, and there, if you replace this x squared, you don't have another x to cancel out. So, okay, so that u sub method is not going to work. I'm not sure how often we've used this method, if at all, but it's something that we will be using in this chapter. So another idea, if u sub isn't going to work and you have the same degree, numerator and denominator, is to use long division to split the problem up. Right now it's a single fraction. I can use long division to split it into multiple terms and see if I can integrate each term. So what I mean by that is set up x squared plus 0x plus 9, divide that into 4x squared plus 0x plus 0. So 4x squared divided by x squared is 4. You get 4x squared plus 0x plus 36. Subtract it all. So that subtracts to negative 36, and that's a remainder. So I can rewrite the problem as the integral of 4 minus 36 over x squared plus 9. All of that gets a dx. And then that's something we can work with because we can integrate a 4, that becomes 4x. And we can integrate a minus 36 over x squared plus 9. Now it's the same or similar arctangent problem from before. We just have a 36 out in front. So minus 36. The u and the a are the same, so I'm not going to write all this out again, but this becomes times 1/3 arctangent of x over 3 plus c. And of course, we could simplify it. 36 times 1/3, we could make this a minus 12, etc. Okay, so the key in this chapter to begin with is just we're throwing all of our types of integration together, mixing them up, and seeing if you can keep it all straight. Okay, and it just takes practice. It's not something that's like, there's not a tried and true method for all of these. Sometimes you have to apply more than one rule. All right, so, and then other times substitution could come first, or maybe there's like an algebra step first. So we can call these like problems that are in disguised form. So an example here is like this one. I've got the integral of x squared root of 16 minus x to the 6th. Again, there should be a dx that probably got erased right there. Now, if you go up to our list, anytime I see square root of a difference of perfect squares, I'm thinking inverse trig, and this one's inverse sine. But it's not just in the form of like 1 over a squared minus u squared, or it doesn't seem to be. So we just have to be careful with this. Just because that's not an x squared doesn't mean this isn't going to work. X to the 6th is a perfect square. So let's see what this would be if we investigate what a and u would be. All right, so a would have to equal 4 because that's the square root of 16. U would have to equal x to the 3rd because that's the square root of x to the 6th. And then du, we're used to just saying, oh, du is equal to dx, done. But here, du is equal to 3x squared dx. And that's why this x squared is sitting up here. You need the x squared dx. You need a 3 in there. So you're going to put a 1/3 out in front. But you have that little extra u sub step that you have to take care of. All right, so this is actually equal to 1/3 times the integral of 1 over square root of a squared minus u squared du. I always like to write this step because that kind of helps me keep it straight and integrate properly. So I have a 1/3 out here. And then look at your arcsine formula. Arcsine doesn't have the 1 over a right here. It's just arcsine of u over a plus c. So 1/3 was out there because of the u sub. And then arcsine of x cubed over 4, u over a, plus c. So this one we're calling that in disguised form because, yes, it was arcsine, but it was also like a little u sub work that we had to do. All right, what about this one? X plus 3 times square root of 4 minus x squared. Now, it kind of looks like arcsine, except I can't really have arcsine if I have a binomial up here, so that's not going to work. So we have to use one step of algebra to split this up. You have a single term in the denominator, so you are allowed to split this into two integrals. You can say it's the integral from 0 to 1 of x over square root of 4 minus x squared dx plus, there's a 3 here, so plus the integral from 0 to 1 of 3 over square root of 4 minus x squared dx. If you want to put the 3 out in front of your integral, you could do that too. So now it's like two problems in one. So looking at this first term, it's not arcsine again because arcsine du would equal dx, and there's an x up here, so that's a problem. Go back and look at the arcsine formula. It should be a constant over a squared minus x squared if u is just x squared. Okay. So now we go over to u sub. Would u sub work? So in this case, u could equal 4 minus x squared. Du could equal negative 2x dx. That's good. I have x dx. I need negative 2x dx. So if I multiply in a negative 2, I multiply a negative 1/2 out in front. Okay, so the first part is taken care of. I have negative 1/2 times the integral. I'm not going to change my bounds. 0 to 1. This whole numerator is du, so we have 1 over square root of u du. That's something we can integrate. And then what about over here? Plus, I'm going to pull the 3 out in front. Now this is arcsine because u is x and a is 2. And du is dx, and there's no extra x up here to worry about. So that is going to be plus 3 times the integral of 1 over square root of a squared minus u squared du. So when I integrate the first term, I get negative 1/2 times what? This is u to the negative 1/2. So when you add 1 to that, you get positive 1/2. So it's 2 square root of u. Oh, and instead of u, put my expression back in, 4 minus x squared from 0 to 1. And then plus 3, what does this become? This becomes arc sine of u over a, x over 2, from 0, forgot my bounds back there, from 0 to 1. There's no plus c because these are definite integrals. Okay, so negative 1/2. Let's see, when I put in 1, I get 2 square root of 3, and when I put in 0, I get minus. When I put in 0, I get 2 times 2, so minus 4. All right, and my next one, let's see. Sorry, lost my spot there. My next one is times 3, and then let's see, what's arc sine of 1/2? So arc sine of 1/2 should be an angle of pi over 6. Remember, answers for arc sine fall between positive and negative pi over 2. And then minus. Arc sine of 0 is 0. So now I'm getting, distribute this through, negative square root of 3 plus 2 plus pi over 2. And I would just kind of leave it in that form. Yeah, I don't see any reason to switch that around. All right, example 3. Integral of cotangent of x and the natural log sine x. So we're trying to do u sub here. Seems like we would pick the more complicated value to be u sub. So u would be natural log of sine x, and we'll see if we can get du to be cotangent x. So if that's u, then du dx would be 1 over sine x. And then what's the derivative of sine x? That's cosine x. Cosine over sine x is cotangent x, so that's great. So we have cotangent x dx, so that is du. So now we have the integral of u du. Integral of u du is u squared over 2 plus c. And back to what u was. When you're squaring a natural log, you just kind of have to write it like this. Square the entire thing over 2 plus c. Now we could check our work, right? Because we should be able to take the derivative of our antiderivative and get back to our same thing. So let's do that. Let's take the derivative of this. We would get 2 times natural log of sine x over 2. 2 times that over that. That's power rule. And then chain rule times 1 over sine x. Chain rule again, derivative of sine is cosine x. Okay, so the 2's cancel out. Natural log of sine x times cotangent x. That is what the original problem was. So yeah, so your answer checks out. Okay, what about example 4? Tangent squared of 2x dx. So we have tangent squared. That's not the derivative of anything. So maybe we need to try some, like one of our identities. What is tangent squared equal to? Sine squared over cosine squared. Okay, but that doesn't really help me either because they're squared. So our other identity involving tangent squared could be secant squared 2x minus 1. Okay, so now we have the integral of secant squared. Secant squared is something's derivative, right? It's the derivative of tangent. So all I need is a little bit of u sub to take care of this. So if u is 2x, du is 2 dx. I don't have a 2, so if I want a 2 in there, I've got to put a 1/2 out here. Sorry, I should have probably split this up. But so for my first part, I've got 1/2 the integral of secant squared u. Well, let me write this out. 1/2 the integral of secant squared u. I want to be more thorough here. And then the 1/2 does not apply to the minus 1, so minus the integral of dx. All right, so this part, I have my u taken care of. This is 1/2 tangent of what was u? 2x. And then this becomes minus x. I'm sorry. No, yeah. Minus x for just that term. And then it's plus c because it's an indefinite integral. All right. So sometimes there are just things that we have to be careful of and things that we need to just try. Things you're allowed to do in these problems. You are allowed to expand or FOIL a numerator if that helps. Okay. That often helps for problems like e to the x plus 1 squared. You might want to square that out to e to the 2x plus 2e to the x plus 1. That might be something that's easier to integrate those separate terms then. It might be helpful to separate out a numerator. So like we did in example, we did that somewhere. Example 2. I'm just going to reference that. Example 2. Complete the square, that's kind of tricky. We don't do that all the time, but that would be, here's an example of when you might complete the square. You've got the square root of 2x minus x squared, and there's no way that u sub works in that problem. It might be better to complete the square on that. So let's see, what would that look like? Completing the square. Negative x squared minus 2x, you factor a negative out so that you can complete the square. Opposite of b over 2 becomes plus 1 when you square it. And then if you just added 1 in here, you really subtracted 1. So keeping on the same side, you add 1 to balance things out. Minus 1 plus 1 balances out. How does that help you? It gives you the square root of negative x minus 1 squared plus 1. And then if you had a u sub, if u is x minus 1, du is dx, and there wouldn't be any other variables in the way. It's kind of hard to just make up part of a problem and show you, so you'll just kind of have to see as we go through the homework how to do this. Divide improper rational, so this is just long division like we did in the front. You might need to add and then turn around and subtract terms in the numerator to make things nicer. Use trig identities, we did that. Multiply by the conjugate, so that's often when radicals are involved. And again, a lot of these tricks, I just kind of want you to go through the homework in the next few days and see how I've used those. All right, so we're going to stop here for today.